Time is one of those things everyone thinks they understand until they actually try to explain it. Ask any person on the street what time is, and they'll confidently say something like, "It's, well, you know, time." And that's fair. We live inside it, schedule our lives around it, worry about running out of it, and celebrate when we think we have plenty of it. Yet, when we look closely, time turns out to be strange, slippery, and almost annoyingly complicated. Hi there, and welcome to Sleepy Space Traveler. I'm really glad you're here, and I hope this moment of time can become a gentle pause in your day. This channel was created as a quiet space for anyone who enjoys falling asleep to calm storytelling, peaceful narration, and soft explorations of science, the universe, and the mysteries around us. Here, we slow everything down. We take big ideas about space, time, reality, and existence, and turn them into simple, soothing stories you can drift off to. If this kind of content helps you relax, unwind, or fall asleep a little easier, I would really appreciate it if you could like this video and subscribe to the channel to help more people discover this space, and help us continue creating these nightly journeys. Please let me know in the comments where you're watching from. And, of course, because in this video we're going to talk about time, so I would really want to know what time it is for you right now. Thank you very much for being here. Now, let's begin. Physics, in particular, has a way of taking things that feel intuitively obvious and turning them inside out. Time is no exception. In everyday life, time seems simple. 1 second follows another, minutes stack into hours, tomorrow comes after today, and nobody ever celebrates their birthday twice in the same year, no matter how hard they try. But as soon as we ask deeper questions, what is time made of? Why does it only move forward? Does the universe have a clock? Why do different clocks disagree when moving fast or sitting in strong gravity? The answers become far less tidy. If anything, the more science progresses, the weirder time becomes. Classical physics treats time like a universal background rhythm. Einstein showed it bends and stretches. Quantum mechanics doesn't seem to know what to do with it at all. Cosmology hints that time might have had a beginning, and quantum gravity whispers that time may not fundamentally exist. Somewhere between all these ideas lies a concept we use every single day, usually without questioning it. Before we dive into the physics, it helps to acknowledge something. The human experience of time is not physics. It's biology, psychology, and a little bit of personal drama. Our brains have their own way of processing time, and that subjective experience often misleads us. Think about how slowly time moves when you're stuck in line at the DMV, or waiting for a download that claims it will take 5 minutes, but clearly means something closer to forever. Compare that with how fast a weekend seems to disappear, or how years can feel shorter as we get older. The physics of time doesn't speed up or slow down depending on how interesting your day is, but your brain absolutely does. Psychologists have found that our perception of time is tied closely to attention. When you're bored, you notice every small moment, like counting tiles on the ceiling or listening to the distant hum of an air conditioner. Your brain logs more information per second, making time feel stretched. When you're busy or emotionally engaged, your brain compresses the moment into fewer timestamps, so the hours feel like minutes, This is why some memories feel longer or shorter, depending on emotional weight, novelty, or stress. A child's year feels endless because almost everything is new. An adult's year feels short because routines compress the experience. None of this is related to actual physics. It's simply how our brains build their internal timeline. Biology gets involved too. Humans run on internal clocks, circadian rhythms, hormonal cycles, neural oscillators. Even without sunlight or clocks, our bodies attempt to keep a 24-hour rhythm. Astronauts on the International Space Station drift slightly out of sync if not kept on strict schedules. Your body, in other words, is trying its best to be a clock, just not a very precise one. This immediately shows why studying time scientifically is tricky. The first clock we ever used was ourselves, and we are unreliable narrators. Because humans quickly realized they were terrible timekeepers, the earliest civilizations looked upward and turned the sky into a clock. Day and night, seasons, the movement of stars. These were predictable and shared by everyone. Sundials marked the passage of time using shadows, which was convenient right until it wasn't. Like on cloudy days or at night or during those awkward moments when someone stood in the wrong place and ruined the measurement entirely. Water clocks followed, then candle clocks, then mechanical clocks with gears and springs. These were huge advances, but they drifted constantly, requiring constant recalibration. The Industrial Revolution pushed timekeeping into hyper-importance. Trains, factories, and communication networks demanded precision. That led to quartz clocks, which vibrate at a stable frequency, and eventually atomic clocks, which are accurate enough that they would lose less than a second over the entire age of the universe. Why does this matter for understanding time itself? Because each technological upgrade subtly changed our concept of time. The more precisely we measured it, the more clearly we discovered that time doesn't actually behave uniformly. The universe wasn't the problem. Our assumptions were. If you lived before Einstein, you'd probably think that time ticked the same for everyone in the universe. Why would you think otherwise? Your neighbor ages at the same rate you do. Your clocks agree within reasonable limits. Even the planets appear to follow predictable cycles. But this is like trying to judge the shape of the Earth while standing in your backyard. Everyday experience is too limited to reveal the deeper structure. Einstein's work showed that time depends on motion and gravity. Move fast enough, and your time slows down relative to someone at rest. Stand near a massive object like a planet or a black hole, and your time also runs slower compared with someone farther away from that mass. Time, in other words, is not a universal beat. It's a stretchy, malleable dimension. This has been tested repeatedly, with atomic clocks on airplanes, satellites, mountaintops, and in laboratories. Time dilation isn't a theory waiting to be confirmed. It's a fact so reliable that your GPS uses it daily. Without correcting for time dilation, GPS would be wrong by miles within minutes. So already we have a problem. The thing humans thought was simple for thousands of years turns out to be dependent on speed and gravity. But that's only the beginning. In physics, especially in relativity, time is woven into space-time. It's not separate from space, it's another dimension with its own rules. When we measure distances and durations, we are measuring the geometry of space-time itself. This means events are not placed in a universal timeline, but in a four-dimensional structure, where different observers can disagree on what happened first or at the same time. This is deeply unintuitive from a human perspective, which expects time to be a single shared stage on which everything plays out. Meanwhile, quantum mechanics treats time as an external backdrop, something that flows uniformly, independent of particles and fields. This clashes with relativity, where time is flexible and shaped by mass energy. And when physicists try to merge both theories to create a theory of quantum gravity, time becomes even stranger. Some equations suggest the universe at a fundamental level may not have time at all, only relationships between states. Time, in this view, might be an emergent phenomenon, a kind of illusion arising from deeper rules. So the question, what is time, becomes similar to asking, what is temperature, before thermodynamics existed. People could feel temperature long before they understood that it came from the kinetic energy of atoms. In the same way, we experience time, but the underlying machinery might be far more complex than we thought. Time is such a foundational part of physics and cosmology that understanding it has consequences everywhere, from how the universe began to how it might end. It affects black holes, the expansion of the cosmos, particle behavior, entropy, and even the origin of life. You don't need a PhD to appreciate these concepts. You only need curiosity and patience, and perhaps a willingness to let go of intuition for a moment. This video will explore time from all angles. Why we perceive time the way we do. How classical physics viewed time. How relativity changed everything. Why quantum mechanics makes time confusing. How entropy gives time its direction. Why cosmology implies a beginning of time. Whether time is real or merely a useful invention. And whether time travel is theoretically possible. Each section will build on the last, using analogies and examples drawn from everyday life. You'll see why eggs don't unbreak, why astronauts come home younger, why black holes stretch time like chewing gum, and why physicists sometimes argue about whether the past and future actually exist. But more importantly, by the end of all this, you'll have a clearer understanding of why time, something so ordinary and constant in your life, is one of the universe's most extraordinary puzzles. Now that we've acknowledged the problem, that time feels simple but isn't, we can start peeling back the layers. In the next part, we'll look at how physics historically approached time, how clocks reshaped our understanding, and why Einstein's discoveries changed the entire structure of the universe. If you want to understand why modern physics treats time the way it does, you have to start with the worldview that came before it. A worldview so solid and intuitive that it shaped scientific thinking for over 2 centuries. That worldview belonged to Isaac Newton. Newton saw time the same way most people do before physics ruins everything. Steady, absolute, and entirely indifferent to the events unfolding inside it. To Newton, time was like a perfectly reliable cosmic grandfather clock ticking in the background of the universe. It didn't run fast or slow. It didn't stretch or wrinkle. It didn't care whether you were standing, running, climbing a hill, or orbiting a star. Time, in Newton's picture, was the calm, impartial stage on which the drama of physics played out. His famous phrase captured it neatly. Absolute, true, and mathematical time flows equably without relation to anything external. That's an elegant way of saying time marches forward at a single universal pace, no matter what. This idea fit beautifully into the physics of the 17th and 18th centuries. Newton's laws described how objects moved, fell, collided, and orbited. If you wanted to predict motion, you just plugged in a time variable that ticked uniformly. Planets moved through space as if sliding across a fixed timeline. Cannonballs arced through the air according to a single cosmic stopwatch. And for a long time, this model worked extremely well. Humanity went from believing Earth was at the center of everything to predicting planetary positions with exquisite precision. Navigation improved, engineering flourished. Time, as Newton imagined it, became the backbone of classical mechanics. But a strange pattern began to appear. The more precisely physicists tried to measure how nature behaved, the more cracks they found in this idea of universal time. One of the quietly delightful things about physics is that sometimes the universe drops hints long before anyone understands them. In the 1800s, as clocks became more accurate, people noticed that clocks in different parts of the world, even when carefully synchronized, began to drift out of sync. This wasn't due to mechanical problems. It wasn't due to temperature differences. It wasn't due to lazy clockmakers in certain countries. Instead, the culprit was something more subtle. Earth is a spinning object, and the sunlight we observe reaches different locations at different times. Before time zones were invented, this caused massive confusion for railways, telegraphs, and early scheduling systems. But even after standardizing time zones, a deeper problem remained. When two clocks moved relative to each other, or when one experienced stronger gravity, they no longer agreed perfectly. These effects were so tiny that 19th century scientists dismissed them as measurement noise. They were not noise. They were early glimpses of Einstein's revolution. Albert Einstein did not begin his scientific career intending to rewrite the nature of time. He was trying to fix inconsistencies in electromagnetism. Yet in doing so, he ended up dismantling Newton's universal clock entirely. The key idea behind Einstein's special relativity is surprisingly simple. The speed of light is always the same, no matter how fast you're moving. That sounds harmless. But mathematically, this breaks Newtonian time completely. If the speed of light must remain constant for all observers, then distance and time must adjust themselves accordingly. Enter the now famous consequences. Time dilation. A moving clock runs slower than a stationary one. Length contraction. Objects shrink along the direction of motion. Relativity of simultaneity. Two events that appear simultaneous to one observer may not be simultaneous to another. Suddenly, time was no longer a rigid, universal rhythm, but a flexible quantity that changed depending on your velocity. If you and your friend each carried a perfectly precise clock and one of you took a high-speed trip around the world, the two clocks would disagree afterward. One of you would simply have aged less. This isn't philosophical. It's real, it's measurable, and it's been tested countless times. Imagine time not as a straight road, but as a highway with multiple lanes. If you drive slowly, you stay mostly in your own lane. Your experience of time is normal. But if you move close to the speed of light, you start merging into adjacent lanes where the rules differ. Your watch ticks more slowly. your biological processes slow down. From your perspective, everything seems normal, but everyone else insists you're aging more slowly than they are. Your friend waving at you from the sidewalk disagrees with your measurement of time, not because either of you is wrong, but because time itself bends around your motion. Newton would have hated this analogy. Time dilation has been tested so thoroughly that, at this point, it's one of the most confirmed predictions in physics. Some examples. 1. Atomic clocks on fast airplanes. In the 1970s, scientists flew highly precise atomic clocks around the world on passenger jets. When compared with identical clocks that stayed on the ground, the flying clocks had lost time, exactly as Einstein predicted. 2. Muons in particle accelerators. Muons, tiny subatomic particles, normally decay very quickly. But when they travel close to the speed of light in accelerators, their decay slows dramatically. They experience time differently. 3. GPS satellites. Your smartphone relies on orbiting satellites to determine your location. These satellites experience two time effects simultaneously. They're moving fast. Time should slow down for them. They're in weaker gravity than Earth's surface. Time should speed up for them. Engineers must correct for both effects. Otherwise, GPS would drift by kilometers per day. In other words, Einstein is literally embedded inside your phone. Just when physicists were getting used to time being dependent on motion, Einstein introduced general relativity, a theory that bent space and time into a single flexible fabric. Space-time. In this picture, gravity isn't a force pulling objects together, as Newton thought. Instead, massive objects like planets and stars curve space-time, and objects move along these curves. This has a consequence for time itself. The stronger the gravity, the slower time passes. This means time moves slightly faster at the top of a skyscraper than it does on the ground. Astronauts on the International Space Station age slightly slower than people on Earth due to motion, but also slightly faster due to weaker gravity. GPS satellites run faster than ground clocks because they feel less gravitational pull. Near a black hole, time can slow almost to a halt relative to distant observers. If you watched a clock fall into a black hole from a distance, it would appear to tick slower and slower until it practically freezes at the event horizon. This isn't science fiction, it's physics. Imagine laying a mattress flat. Place a marble on it. It stays still. Place a bowling ball, the mattress sags. Now, put the marble near the bowling ball. The marble rolls toward it, not because the bowling ball pulled it, but because the surface is curved. Time behaves similarly on this mattress. A clock sitting near the bowling ball, a massive object, experiences dips in the mattress, meaning time slows. A clock farther away, on flatter regions, runs faster. The universe doesn't hand out equal time to all clocks. Where you are and how you're moving matters. One of the hardest concepts for beginners to accept, not because it's mathematically complex, but because it insults our intuition, is the idea of simultaneity. We assume two events either happen at the same time or they don't. If lightning strikes two trees simultaneously, surely everyone in the universe agrees, right? Nope. Special relativity says simultaneity is relative. Two observers moving differently may disagree about whether those strikes were simultaneous, and neither is wrong. The structure of space-time itself means simultaneity has no universal meaning. this becomes extremely important for understanding. Time travel, causality, the block universe model, and whether the past and future exist simultaneously. We'll return to these later. Newton's model excelled at describing the world of everyday objects: apples, cannonballs, horses, planets. In that domain, time is nearly absolute. A person walking down a street does not need to worry about time dilation changing their age dramatically. But as measurement accuracy increased, and as we studied fast-moving and extremely massive systems, Newton's time produced errors that could no longer be ignored. Einstein's model fixed these errors by redefining time not as something separate from space, but as something intertwined with it. Instead of an independent backdrop, time became one dimension of a dynamic, geometry-shifting universe. What once seemed solid became flexible. What once seemed universal became personal. What once seemed simple became, well, deeply weird. Einstein's redefinition of time did more than advance physics. It reshaped our understanding of the universe's architecture. It made the Big Bang model possible. It predicted black holes and gravitational waves. It forced cosmologists to consider the evolution of space and time together. It laid the foundation for modern astrophysics. And, on the practical side, GPS works. Particle accelerators work. Satellite communications work. Modern electronics rely on relativistic corrections, all because time does not behave the way Newton thought it did. By the early 20th century, humanity learned that time was relative, stretchable, dependent on speed and gravity, woven into space-time geometry. But this is only half the story. Because as we turn toward quantum mechanics, the theory governing atoms, fields, and particles, we encounter a completely different interpretation of time. One so incompatible with relativity that physicists have spent decades trying to combine them. The next part dives into that conflict. If you're ready, by the time physicists finished digesting Einstein's relativity, the universe had already prepared another surprise. Just as relativity showed that time could stretch, bend, and disagree with itself depending on gravity and motion. The emerging field of quantum mechanics introduced a second, very different style of time. One that behaves so strangely that even physicists joke about it being nature's way of telling us we know nothing. Quantum mechanics governs the behavior of atoms, electrons, photons, quarks, and all the other microscopic building blocks that make up everything. And unlike relativity, which treats time as part of space-time's fabric, quantum mechanics treats time as, well, something much simpler. In quantum theory, time is just a parameter, a number, a label in an equation. It doesn't stretch. It doesn't slow down. It doesn't interact with matter. It just flows uniformly, like Newton originally thought. In other words, quantum mechanics uses Newton's rigid time, while relativity uses Einstein's flexible time. This is a bit like watching two experts at a conference present completely different definitions of the same word, and both insist they're correct. So, what is time in quantum mechanics, and why does it behave so differently from time in relativity? Let's unpack this very gently. In the quantum world, objects are described by mathematical entities called wave functions. These wave functions evolve according to something called the Schrödinger equation. If you've never seen it, think of it like the cosmic equivalent of a bread recipe. Add energy. Stir in probability. Let it rise over time. Bake until measurement collapses the wave function. The Schrödinger equation includes a t representing time. But here's the catch. Time is not influenced by the particle. Time never changes its rate. Time is not random. Time does not participate in quantum uncertainty. Quantum systems can be uncertain about position, momentum, energy, spin, and many other things, but not about time. In quantum mechanics, time is given, something external, something you do not question. It's the equivalent of watching a movie where everything is unpredictable except the speed at which the movie runs. This leads to a fundamental mismatch. In relativity, time is dynamic and intertwined with space. In quantum mechanics, time is fixed and external. This contradiction is not a minor detail. It's the biggest reason physicists struggle to create a theory of quantum gravity. Put simply, we have two of the most successful theories ever created, and they define time in incompatible ways. One of the most peculiar aspects of quantum mechanics is superposition, the idea that a particle can exist in multiple states at once until measured. An electron can be in two places. A photon can go through two slits. An atom can spin up and down simultaneously. But here's the weird part. Superposition evolves over time in a perfectly smooth, predictable way. Probability spreads. Amplitudes change. Wave functions ripple like water. Quantum uncertainty is not chaotic or random until you measure it. Once measured, though, the superposition collapses instantly. And instant is where time gets tricky. Quantum mechanics has no problem with instantaneous effects. Relativity absolutely forbids anything happening faster than light. This disagreement creates philosophical headaches. If collapse is instant, then what does that even mean for time? From whose perspective is it instant? How can instant exist in a relativistic universe where simultaneity is relative? Once again, time shows up wearing two different hats, and neither theory can force it to choose one. Does quantum mechanics even need time? Believe it or not, some physicists have proposed that the universe might not need time at all, or at least not in the way we experience it. One famous attempt comes from John Wheeler and Bryce DeWitt, who developed an equation that describes the entire universe as a quantum object. Their surprising result? The fundamental equation of the universe contains no time variable, no t, no ticking clock, no arrow of time, no past evolving into a future. This is not a typo. It's a real consequence of treating the entire cosmos quantum mechanically. So, how do we get time back? Some physicists propose that time emerges from the relationships between quantum variables. Time, in this view, is not fundamental. It's something that appears due to correlations between objects. Think of it like this. If everyone in your neighborhood starts turning on their porch lights at night around the same hour every day, you can infer an underlying time, even if no one has a clock. Time becomes a pattern, not a literal thing. This idea is still debated, but it highlights something profound. Time might not exist at the most fundamental level. It may be something that emerges, like temperature or pressure. Quantum entanglement is often described as spooky action at a distance, Einstein's least favorite phrase. When two particles are entangled, measuring one instantly determines the state of the other, even if they're on opposite sides of the galaxy. Again, we confront a tension. Quantum mechanics, instant correlation. Relativity. Nothing can be instantaneous, but entanglement does not transfer information faster than light, so relativity isn't violated. Still, it raises a question. Do entangled particles share a kind of internal time different from our external time? Some researchers believe entanglement might be the key to understanding how time emerges, why time flows, why the universe has a direction, past, future. There are emerging theories where time is a byproduct of entanglement increasing, a sort of cosmic bookkeeping system that tracks relationships between particles. Imagine a giant dance floor where every dancer is linked to others by invisible threads. As the dance becomes more complex, the pattern of connections produces the sensation of time moving forward. That's one of the leading modern views. Time is what happens when quantum correlations evolve. The uncertainty principle tells us that certain pairs of physical properties, position and momentum, energy and time, cannot both be known precisely. This leads to a fascinating twist. Although quantum mechanics treats time as a clean external parameter, particles still experience a kind of time-related uncertainty. For example, a particle that exists only briefly can borrow energy from the vacuum. Virtual particles pop in and out of existence for extremely short durations. Energy fluctuations intensify at very small time intervals. This relationship between time and energy is not full uncertainty in time itself, but it hints that even in quantum theory, time is not as simple as it first appears. It's as if the universe cannot decide whether time is sacred or negotiable. One of the strangest unresolved questions in quantum mechanics is, when does a possibility become a fact? Before measurement, a particle is spread out over probabilities. After measurement, it's found in one location. But when does that transition occur? Quantum mechanics works with two very different types of time evolution. 1. Smooth evolution, governed by the Schrödinger equation. 2. Sudden collapse, triggered by measurement. These two processes obey different rules and may not be compatible with a single universal time. Some interpretations suggest collapse is not real. Everything evolves smoothly forever. The universe splits into multiple branches, Everett's many worlds. Consciousness triggers collapse. Gravity triggers collapse. Information triggers collapse. Each version uses time differently. Imagine a theater play where the first half of the script is written in English and the second half in French, but they describe the same events. The actors can perform both halves, but no one agrees on which one is real. That's quantum time. Relativity suggests a block universe, where past, present, and future all exist simultaneously in a four-dimensional structure. Time does not flow. Our consciousness moves through it. Quantum mechanics, however, seems to insist on genuine randomness, unfolding probabilities. The future not existing until measured. Reconciling these two pictures is one of modern physics' greatest challenges. Some physicists argue the block universe is right, and quantum randomness is just ignorance. Quantum mechanics is right, and relativity's block universe is incomplete. Both are approximations of something deeper. What everyone agrees on is that quantum mechanics exposes cracks in our classical understanding of time. It suggests time may not be fundamental, time may not flow, and time may not be a single universal experience. Instead, it might be something that emerges from entanglement, appears due to correlations, changes depending on measurement, collapses or splits, behaves differently at different scales. Time in quantum mechanics is like software written on top of hardware we don't fully understand. Since relativity uses flexible, geometric time and quantum mechanics uses rigid, external time, merging them into one theory is notoriously difficult. This challenge is known as the problem of time in physics. There are several candidate solutions. 1. Loop quantum gravity tries to quantize spacetime itself, suggesting time might be made of discrete ticks. 2. String theory suggests time emerges from vibrating strings and higher dimensions. 3. Causal set theory frames spacetime as a network of discrete events connected by causal relationships. 4. Emergent time. Theories propose that time is like temperature, not fundamental, but something that arises from many interacting components. All of these attempt to answer the same question. How do we make quantum time and relativistic time play nicely together? So far, no one has succeeded completely. Why this matters? Understanding quantum time isn't just philosophical. It has real stakes. It affects how we model black holes. It shapes our understanding of the Big Bang. It determines what before the universe means. It influences attempts at time travel models. It affects quantum computing and ultra-precise clocks. It changes how we think about causality and free will. Time is not just a label we attach to physics, it's built into the foundations of reality. And until we unify relativity and quantum mechanics, we won't know which version of time is truly correct. The next part will explore where these ideas meet cosmology, the origin of time, the arrow of time, and why the universe seems to move from past to future instead of the other way around. If you've made it this far, congratulations! You've already survived the weirdest parts of time, relativity stretching it, quantum mechanics ignoring it, and physicists debating whether it even exists. Now we get to one of the most intuitively obvious yet scientifically confusing aspects of time. Why does time have a direction? It's such a familiar feature of life that we barely notice it. Eggs break but do not unbreak. Coffee cools down but does not spontaneously heat up. People age forward and not backward, no matter how many skincare products they buy. Yet, when you look at the laws of physics, the deep, fundamental ones, they don't actually forbid eggs from unbreaking, coffee from heating itself, or people from getting younger. That's right. Most of the major equations of physics work perfectly well both forward and backward in time. So, why doesn't reality behave that way? Why does time move from past, future, instead of the other way around? This directionality is known as the arrow of time, and understanding it requires digging into several separate pieces of physics: thermodynamics, statistical mechanics, cosmology, entropy, and even quantum information. Let's take them step by step, using as few headaches as possible. The most famous explanation for the arrow of time comes from the second law of thermodynamics. Entropy, a measure of disorder, tends to increase in an isolated system. Entropy going up provides a natural direction. Order, disorder, low entropy, high entropy, simple, complex. To make this practical, let's start with a simple analogy. A room full of air. Imagine opening a door between two rooms. One room full of air, one room completely empty. The air molecules rush from the full room into the empty one, scattering and spreading out until they are evenly distributed. Have you ever seen the reverse happen? Air spontaneously gather itself back into one room, leaving the other empty? Probably not. In fact, seeing that happen would violate what we consider the statistical bedrock of reality. But here's the curious part. The laws of physics do not forbid it. If you tracked each individual molecule, it could, in principle, bounce around in exactly the right pattern to recollect all the air molecules into the original room. It's just so astronomically unlikely that you'd need to wait longer than the age of the universe for it to occur naturally. This is the key insight. The arrow of time comes from probability, not from fundamental laws. Low entropy is unlikely. High entropy is incredibly likely. Given enough room, enough molecules, and enough energy, disorder dominates. Time, therefore, seems to move forward, because that's the direction in which entropy almost always increases. Why did the universe start with low entropy? If entropy always increases, then the universe must have started at an extremely low entropy for things to unfold the way they did. And indeed, that appears to be true. The early universe, right after the Big Bang, was extremely hot, extremely dense, extremely uniform, and uniformity means low entropy for gravity. This may sound counterintuitive, because we tend to think of uniformity as boring, and therefore high entropy. But gravity plays by its own rules. Gravity wants clumps. Gas clouds collapse into stars. Stars gather into galaxies. Galaxies cluster into superstructures. Gravitational entropy increases when matter clumps together, because clumping releases energy, heat, light, radiation, and because the number of possible clumping configurations is enormous. So, a perfectly smooth universe is actually a very low entropy arrangement from gravity's perspective. Which means the biggest mystery is, why did the universe start so smooth? If the arrow of time is the march toward higher entropy, then the Big Bang must have been the lowest entropy moment the universe has ever experienced. And that leads to one of the most difficult open problems in physics: the past hypothesis. Physicists call it the past hypothesis. The universe began in a very low entropy state. This is not really an explanation. It's more like a foundation statement. But it sets the stage for everything. Stars forming, galaxies spinning, life evolving, time moving forward. Without low entropy at the beginning, the universe would have been born old, with no arrow of time for us to experience. Why the Big Bang had low entropy remains a mystery debated by cosmologists, philosophers of physics, quantum gravity researchers, people who write very long papers no one reads. We don't yet know the answer, but the question is central to understanding what time is. Another way to think about the arrow of time is through memory and information storage. Ask yourself, why can you remember the past but not the future? Why can you track cause, effect, but not effect and cause? Why do fossils record what happened millions of years ago, but not what will happen millions of years from now? The answer, once again, comes back to entropy. Whenever a system evolves, it leaves traces in higher entropy states. Footprints in sand. Ash left by a fire. Data on a computer. Neurons in a brain storing memories. All of these are irreversible processes that scatter energy and increase entropy. Memory requires entropy production. If making a memory decreased entropy, your brain would violate thermodynamics every time you formed a thought. Instead, each act of memory increases entropy in the environment around you. This asymmetry creates another arrow of time. We remember the low entropy past because physical records form as entropy increases. This is why you cannot remember the future. The future hasn't left any physical trace yet. Let's zoom out. Cosmology gives us another arrow of time, expansion. The universe is expanding, and not gently either. It's accelerating, driven by something we call dark energy. Distances between galaxies grow larger every second. Even if we forgot about entropy, the expansion alone provides a directional sense of time. Smaller universe, earlier, larger universe, later. However, the expansion alone doesn't fully explain the arrow of time, because physics can still run backward in an expanding universe. It would just shrink everything. The expansion helps reinforce our perception of time, but doesn't define it. Yet, when combined with entropy, expansion gives us a clearer story. The early universe was smooth because it was small. As it expands, gravitational clumping increases entropy. Therefore, cosmic expansion drives the entropy gradient that creates the arrow of time. So, the universe expanding is not merely a fun trivia fact. It's part of the engine behind why time moves forward at all. Light also contributes to the arrow of time. When you turn on a flashlight, photons move outward. They don't converge inward unless someone plays the video backward. Radiation spreads, heat disperses, energy moves from high concentration, low concentration. This gives us another arrow of time. Waves and radiation move outward into the future. Even more interesting, if radiation behaved the same in both time directions, the universe would be overwhelmed by incoming light focused from the entire cosmos. We'd see starlight converging instead of spreading, heat beams gathering instead of diffusing. The night sky would be blinding. Thankfully, the universe doesn't work that way. When all is said and done, time's arrow boils down to probability, initial conditions, the overwhelming dominance of disorder over order. Let's use the simplest analogy possible, a shattered plate. If you drop a plate on the floor, it shatters into pieces. Could the pieces reassemble themselves? Physically speaking, yes. Statistically speaking, absolutely not. There are millions of ways for the plate to be broken. There is only one way for it to be whole. The universe behaves like the plate. Low entropy states, whole plates, are rare. High entropy states, broken plates, are incredibly common. The direction of time, the arrow, points from rare, common, from order, disorder. Gravity magnifies the process. Expansion amplifies it. Quantum mechanics leaves it mostly unaffected. Relativity shapes how we measure it, but none of these fundamentally set the arrow. Entropy does. Do all arrows of time always line up? Interestingly, physicists have identified multiple arrows of time. Thermodynamic arrow, entropy increases. Cosmological arrow, universe expands. Radiative arrow, waves move outward. Psychological arrow, we remember the past. Quantum arrow, measurement collapse. So far, all arrows point in the same direction. Forward. This appears astonishingly convenient, almost suspiciously so. There are deep ongoing debates about whether the arrows all originate from entropy, or they independently arise but happen to align, or they are different manifestations of one deeper principle we haven't discovered. No one knows the final answer, but the alignment itself is one of the greatest clues we have about the true nature of time. What about reversing time? Here's a fun fact. Physicists can reverse time in extremely tiny systems. If you isolate a handful of atoms, protect them from their environment, cool them to near absolute zero, and manipulate them with lasers or magnetic fields, you can make the entropy decrease temporarily. Researchers have done this in laboratories. They watched. Heat flow backward, probability distributions reverse. Microscopic order spontaneously increase. But there's a catch. It only works when the system is tiny. It's extremely isolated. Energy inputs are fine-tuned. Entropy is measured carefully. In other words, it's a laboratory trick, not something the universe does on large scales. The moment you let the system interact with its environment, the arrow of time reappears instantly. You can reverse time's arrow in a toy model. You cannot reverse it in a kitchen, a star, a galaxy, or a universe. Entropy always wins. Why does the arrow of time matter? Understanding the arrow of time helps us answer major questions. Why is the universe structured the way it is? Because time moves toward disorder, shaping galaxies, stars, planets, and life. Why do we age? Because biological complexity depends on entropy production. Why can we store memories? Because memory formation increases entropy. What happened at the Big Bang? We don't know, but low entropy is central. Could time ever reverse? Not for anything larger than a microscopic laboratory experiment. Could the arrow end? Possibly. If the universe reaches thermodynamic equilibrium, a state called heat death. But don't worry. Heat death is trillions of years away. Even your favorite streaming services won't last that long. Despite time being rooted in entropy, our experience of it is deeply psychological. We feel time passing, organize life around schedules, base identity on memory, fear losing time, anticipate the future. These traits evolved because they helped our ancestors navigate an irreversible world. If drinks unspilled, fires unburned, and predators unpounced themselves, evolution would have looked very different. Humans evolved in a universe where the arrow of time matters, and our minds reflect that. If the arrow of time exists, and it clearly does, then the natural next question is, where did this arrow come from? Did it start at a specific moment? Could it end someday? And does it behave the same way everywhere? Intuitively, we think of time as a long line stretching from one end of eternity to the other. But physics doesn't grant us that luxury. Time, as best we can tell, is tied to the structure and evolution of the universe itself. To understand time fully, we need to examine how it behaves at extremes, near the beginning of the universe, near black holes, inside particle collisions, and in theories that stretch beyond traditional spacetime. Let's walk through those ideas step by step, without losing our sanity. Did time begin at the Big Bang? The standard explanation taught in schools is simple. The Big Bang created time. Before the Big Bang, time didn't exist. This sounds clean and comforting, but it's not the full scientific picture. Instead, modern cosmology takes a subtler view. The Big Bang marks the earliest moment at which our current physical models can describe the universe. But it might not be the absolute beginning of time. To see why, we need to examine what time beginning even means. Time as a coordinate system. In physics, time is treated as a dimension similar to space. Saying that time began is like saying North began. That doesn't quite make sense unless you're referring to the North Pole, the end point of a coordinate system. Stephen Hawking used this analogy famously. Asking what happened before the Big Bang is like asking what's north of the North Pole. It's not that the question is rebellious, it's that the coordinate system simply doesn't extend past that point. But Hawking's view relies on a specific mathematical model, Euclidean space-time. Other models allow time to extend through or beyond the Big Bang. Possibility A. Time truly began. In this scenario, time, 0 at the Big Bang. There is no before, not because it's forbidden, but because the concept simply doesn't exist. The arrow of time emerges as entropy increases from the initial low entropy state. This matches the classic Big Bang picture. Possibility B. The Big Bang was a transition. Maybe the Big Bang wasn't the start, but a transformation. A bounce from a previous universe, a collapse of a higher dimensional structure, a fluctuation in a timeless quantum foam, a branching event in a multiverse, a phase change in space-time itself. In these models, time doesn't begin at the Big Bang, it merely changes character. Possibility C. Time is emergent. This idea, gaining popularity in quantum gravity, claims time is not fundamental. It emerges from deeper physical processes, the way temperature emerges from molecular motion. In this view, asking when time began is like asking, when did temperature begin? Temperature doesn't exist until molecules exist. Likewise, time wouldn't exist until the underlying physical structure that produces it exists. Each possibility leads to different implications about what time actually is, which we will return to shortly. Could time end? If time began, could time stop? The answer, yes, depending on the universe's fate. There are 3 dominant scenarios cosmologists consider. Scenario 1. Heat death, time fizzles out. If the universe keeps expanding and the expansion accelerates, eventually, stars burn out, galaxies drift apart, matter decays, all energy spreads thinly. This leads to maximum entropy. When entropy reaches its theoretical ceiling, the arrow of time loses meaning because, without differences in energy, nothing happens. No events occur, no processes unfold. Time has no direction. Time would not stop dramatically. It would fade into irrelevance. Imagine a movie in which every frame looks identical. Is it still a movie? Technically, yes, but you wouldn't call it time passing. That's heat death. Scenario 2. Big crunch. Time collapses. If gravity eventually overwhelms dark energy, unlikely based on current data but still possible, the universe could reverse expansion and collapse inward. As matter compresses, temperature rises, density increases. Entropy actually falls in gravitational terms. Time, in some models, slows dramatically as the universe approaches final collapse. Some theorists speculate that time could reverse direction, reset, pass through the singularity into a new expansion. This is the basis of cyclic universe models. Scenario 3. Big rip. Time tears apart. If dark energy becomes stronger over time, expansion accelerates exponentially. Eventually, galaxies separate, stars separate from galaxies, planets separate from stars, atoms separate. Even space-time itself rips. At the final instant, called the rip time, space-time curvature becomes infinite, and conventional time loses meaning. This is not a peaceful ending. This is space-time's version of a messy breakup. Black holes are nature's laboratory for breaking intuition about time. According to Einstein's general relativity, the stronger the gravity, the slower time moves. This isn't metaphorical. Clocks actually tick slower near massive objects. So, if you hover near a black hole, not recommended, minutes pass for you. Years pass for distant observers. This effect was famously dramatized in the movie Interstellar, but it's absolutely real. What happens at the event horizon? This is where the weirdness peaks. From your perspective as you fall, you cross the horizon with no drama. Time continues normally. You move toward the singularity in a finite amount of time. From an outside observer's perspective, you never cross the horizon. Your clock appears to slow. You freeze, fade, and redshift into darkness. Both perspectives are correct within relativity. They coexist. That's one of the strangest aspects of time. Different observers can disagree about what events occur and when, yet all remain valid in their frames. Inside the black hole. Here's the part that turns minds into spaghetti. Inside a black hole, time and space switch roles. Moving forward in time becomes equivalent to falling inward. You cannot choose not to fall inward any more than you can choose not to move into the future. The singularity becomes not a place, but a moment in your future, unavoidable as tomorrow. This demonstrates that time is not universal. It depends on the geometry of space-time. Does quantum mechanics have its own clock? While relativity treats time as a flexible dimension, quantum mechanics treats it as a fixed background parameter, a kind of universal stopwatch. This mismatch is one of the biggest challenges in modern physics. Quantum mechanics doesn't give time special treatment. It just assumes time flows and describes how systems evolve inside that flow. But relativity says flow is relative and geometry dependent. Trying to fuse these ideas gives us time in quantum gravity. Many approaches, such as loop quantum gravity and the Wheeler-DeWitt equation, end up producing models where time disappears. The universe is described all at once. Change becomes an emergent property. Time is replaced by correlations between quantum states. This leads to a provocative idea. Time might be an illusion, created by the fact that our brains track change. But illusion doesn't mean fake. It means not fundamental. Fire isn't fundamental, it's chemistry. Temperature isn't fundamental, it's molecular speed. Time might be similar, a useful, powerful byproduct of deeper physics. Could there be multiple timelines? Let's address a popular idea that's surprisingly close to what some physicists take seriously: multiple timelines. Not in the Hollywood sense, no time travelers bumping into their past selves, but in the quantum theoretical sense. The many worlds interpretation, MWI. This interpretation claims every time a quantum event could have multiple outcomes, all outcomes occur. The universe splits into branches. Each branch has its own timeline. Time flows forward in all branches, but the branches never interact. In MAWI, time is still single-directional. Increasing entropy ensures that, but the global set of timelines becomes enormous. Physicists debate whether this branching is real, metaphorical, mathematically useful, or simply too extravagant. But one thing is clear. Quantum mechanics allows a larger variety of possible timelines than classical physics ever imagined. Does time require consciousness? This question sits at the edge of physics and philosophy, but let's treat it honestly. We experience time. We do not observe time directly. We infer its existence from motion, memory, aging, evolution, change. So does the flow of time depend on consciousness? Most physicists say no. Processes occur regardless of observers, but consciousness does shape how we perceive time. Meaningful events feel faster. Boring events feel slower. Fear slows subjective time. Aging accelerates subjective time. Neuroscience suggests the brain constructs time by stitching together sensory data, like a movie editor filling frames between events. So, while consciousness doesn't create physical time, it absolutely creates psychological time. The two are related, but not identical. So, what is time really? Let's summarize what we've learned so far. 1. Time is deeply connected to entropy and the arrow of time, too. Relativity makes time flexible and observer-dependent. 3. Quantum mechanics treats time differently than relativity 4. Cosmology suggests time might have begun or transformed at the Big Bang. 5. Black holes twist time into bizarre shapes. 6. The fate of the universe determines whether time continues indefinitely. 7. Some theories eliminate fundamental time altogether. 8. Our experience of time is partly neurological. 9. The alignment of different time arrows remains one of the biggest cosmic mysteries. With all this complexity, it might feel like physics is avoiding a final answer. But actually, physics is circling around a single profound realization. Time is not one thing. It is a collection of related, emergent behaviors arising from deeper physical laws. Just as life is not one thing, but a set of processes, time may be the same. It is not a universal clock ticking behind the scenes. It is not the same for all observers. It may not be fundamental. It may not be infinite. It may not even exist without space. Instead, time appears to be the way certain physical systems, including the universe as a whole, encode change. When entropy increases, time appears to flow. When gravity bends space-time, clocks distort. When quantum states evolve, probabilities shift. When consciousness forms memories, experience unfolds. Time is the thread connecting all these processes. Not because it is woven into reality from the start, but because it emerges whenever reality changes. By now, we've explored time from almost every angle. Cosmology, relativity, quantum mechanics, black holes, psychology, thermodynamics, and even philosophical edges. But one question still hovers over everything. Is time something the universe must have, or is it something the universe just happens to use? This last part ties everything together. We move beyond specific theories and look at the broader landscape, the shared principles behind them, to understand what time might ultimately be. Why the universe needs time, or just maybe. Physics relies heavily on causality. Cause, effect you. Strike a match, it lights. Drop a ball, it falls. Heat water, it boils. Causality gives physics structure. Without it, laws lose meaning. So, is causality possible without time? Surprisingly, yes, depending on how you formulate the laws. Timeless equations. Many of physics' central equations can be written in a form that has no time variable at all. Examples: the Wheeler-DeWitt equation, quantum gravity, the action principle in classical mechanics, the static solutions in general relativity, certain quantum cosmology models. These equations describe relationships between states, not between moments. In them, time does not tick. It is inferred from correlations between states. The library of states analogy. Imagine the universe as a huge library. Each book are one complete configuration of the universe. No shelf is labeled earlier or later. Time emerges when you read two books in a consistent order. You notice entropy increases between them. There is no absolute ordering, only patterns. This analogy captures modern physics' increasingly common view. Time may not be a universal backdrop. It may be the structure we impose on relationships between states. Einstein gave us a universe where mass bends spacetime, curvature shapes motion, time is woven into the geometry. This picture is extremely successful. GPS relies on it. Satellite clocks drift precisely as relativity predicts. But here's the deeper implication. If space were shaped differently, time would behave differently. Different geometry, different time. Imagine a universe with no curvature, flat, a universe curved like a sphere, a universe curved like a saddle, a universe with extra spatial dimensions, a universe where time itself has curvature. In each case, clocks would tick differently. Motion would unfold differently. The arrow of time might shift. Causality could have different constraints. Physics doesn't treat time as a universal ingredient. It treats a time as a product of geometry. This is why cosmology cares deeply about the universe's shape. It's not aesthetic. It determines what time can do. Closed time-like curves, CTCs. Some geometries, like Gödel's rotating universe or the region around certain wormholes, permit loops in time. A closed time-like curve is a path that loops back to itself. You return to your own past. Do we live in a universe with CTCs? Almost certainly not. Our universe shows no large-scale rotation, and CTC-friendly geometries require extreme exotic conditions. But the mathematics tells us time is not fixed. Time does not necessarily move forward. Time direction can emerge from geometry. This flexibility suggests that time's behavior is not a universal law, but a feature of the particular universe we inhabit. Quantum mechanics introduces something shocking. Many processes do not specify which direction time flows. If you record a quantum event, like electrons exchanging photons, the video essentially looks the same backward. This symmetry suggests, at fundamental levels, time doesn't flow. Instead, systems exist in states defined by probabilities. Before and after come from how we interpret these shifts. But our larger world clearly does have direction. So the question becomes, how does irreversibility emerge from reversible physics? This is one of the deepest open problems in science. Many physicists believe it comes down to initial conditions, entropy, information processing, the structure of quantum measurements. Let's break those down. Initial conditions. The universe started very ordered. If the early universe had been high entropy, then no arrow of time would exist. The universe would be static. Complexity wouldn't form. No stars, no galaxies, no chemistry. The low entropy beginning is what gives us direction. When you wind a clock, the gears then unwind naturally. The Big Bang wound the universe. Entropy. Order decays. Complexity grows. Time moves. Entropy isn't a force pulling us forward. It's the measure of how many microstates a system can occupy. Low entropy, few states. High entropy, many states. Systems evolve toward more states because it's statistically overwhelming. This statistical tilt gives us memories, aging, cause, effect, time that feels like it flows. Entropy provides the illusion of flow, even though microscopic laws are reversible. Information. Losing track of details creates an arrow. Physics is increasingly gravitating toward the idea that time is deeply tied to information. When systems interact, information is lost to the environment. Disorder increases, correlations decay. Entropy rises. This gives rise to a sense of past and future. The more information disperses, the more irreversible processes appear. Quantum measurement. Collapse creates asymmetry. In the Copenhagen interpretation, before measurement, multiple possibilities. After measurement, one outcome. This transition isn't symmetric. You can't unmeasure something. Even if quantum states evolve reversibly, observations introduce a one-way street. Some physicists believe this is where time's arrow originates. Does time flow, or do we move through time? This question seems philosophical, but it's deeply physical. Block universe, eternalism. In relativity, time is treated like space. All moments exist at once. Past, present, and future all coexist. Flow is an illusion of consciousness moving along the timeline. In this picture, you are a 4D being. Your entire life is laid out in space-time. The present is just the point your consciousness perceives. It sounds strange, but this view is extremely compatible with Einstein's equations. Growing block universe. Past exists. Present exists. Future is not yet real. This matches how many people intuitively experience time. Presentism, only the present exists. Past is gone. Future is unreal. This feels intuitive, but conflicts with relativity. Physics today leans toward the block universe, not because it's emotionally satisfying, but because the math fits. But exactly how consciousness experiences a now inside a static space-time remains unresolved. Could time be an illusion? Some of the most influential physicists, including Julian Barber, Carlo Rovelli, and Sean Carroll, argue that time as we perceive it is not a basic property of reality. Instead, reality is a set of interconnected configurations. Time is the way we describe transitions between them. Our brains impose ordering because memory requires sequence. The brain is a time machine. Your brain stores memories, anticipates outcomes, compresses experiences, aligns sensory streams. This produces the sensation of time flowing smoothly. But if your brain didn't create this narrative, you wouldn't perceive time the way you do. Just like vision constructs a stable world from shaky eye movements, time perception constructs a stable now from discrete sensory events. Physics and neuroscience increasingly align on this point. Time is partly physical, partly cognitive. To truly understand time, we need new tools. Here are the major paths forward. 1. Quantum gravity experiments. We need direct tests of physics at tiny scales where quantum mechanics and gravity overlap. For example, tabletop experiments with quantum superposition of small masses. Gravitational decoherence tests, experiments probing spacetime discreteness. These could show whether time is continuous or discrete, is fundamental or emergent, interacts with gravity at quantum levels. 2. Black hole observations. Black holes are time laboratories. With the Event Horizon Telescope and future observatories, we can examine time dilation near horizons, information loss behavior, evaporation dynamics. This could clarify whether time is destroyed, preserved, or transformed inside extreme gravity. 3. Cosmological measurements. Highly precise studies of cosmic microwave background, large-scale structure, expansion rate, early universe fluctuations may reveal whether time had a beginning and whether the arrow of time is tied to cosmic expansion. 4. Simulated universes. Researchers use supercomputers to simulate inflation, black hole dynamics, entropy evolution, emergent spacetime. Some simulations already show time-like behavior emerging from timeless equations. This is one of the most promising paths. After exploring all of physics, what can we say? Here is the closest thing to a consensus. 1. Time is real. Processes depend on it. But it is not universal. Different observers measure different times. 2. Time has an arrow because entropy increases. This arrow might be emergent, not fundamental. 3. Time depends on space-time geometry. Gravity bends time, slows it, stretches it. 4. Quantum mechanics complicates time. It introduces symmetry and timeless equations. 5. Time may not exist at the deepest level. In quantum gravity, time often disappears. 6. Consciousness shapes our subjective time. The brain edits the movie. 7. The universe's fate determines time's future. Heat death, big crunch, or something more exotic. 8. Time is best understood as relationships. Not an invisible river, but the ordering of states. After all the equations, theories, and observations, the current scientific view is time is a structure of change. Where there is no change, there is no time. Where there is change, time emerges naturally. Whether that emergence is fundamental or superficial remains open. But one thing is certain. Understanding time is not just a physics problem, it's a human one. Time shapes memory, identity, meaning, existence. And in studying time, we are studying ourselves. We may one day discover the true nature of time. Maybe it's emergent. Maybe it's fundamental. Maybe it loops. Maybe it branches. Maybe it dissolves at cosmic endpoints. Maybe it's a geometric artifact. But even as physics advances, our experience of time keeps us grounded. We grow. We age. We remember. We anticipate. We wonder. And that human relationship with time, that sense of moving through a changing world, is what makes the question so compelling. Understanding time isn't just about equations. It's about understanding the framework in which all of life unfolds. And that is why physicists continue to chase the mystery. Not because the clock is ticking, but because the clock itself may hold the secrets of the universe.